What if everything you've ever seen, touched, or known is only a fraction of what truly exists? We live our lives believing in 3 dimensions of space and 1 of time. But for over a century, some of the greatest scientific minds have quietly challenged that assumption. Behind the curtain of our everyday reality, there may be realms just beyond our senses, hidden dimensions that shape the cosmos in ways we're only beginning to understand. This isn't science fiction, it's a frontier of modern physics, one where mystery and mathematics meet, and where the rules of reality, as we know them, might just be the beginning. Today, we're setting off on a journey through 20 of the most astonishing discoveries that point toward the existence of these unseen dimensions. From the way entire galaxies spin faster than they should, to strange signals echoing from the edge of black holes, these aren't just abstract ideas, they're real, measurable phenomena that science cannot fully explain without daring to look beyond the world we see. Each discovery is a piece of a vast and intricate puzzle, one that invites us to rethink not only the universe but our place within it. This exploration is for everyone, not just physicists or astronomers, but for anyone who's ever looked up at the night sky and wondered what secrets it holds. These findings challenge us, inspire us, and remind us that curiosity is one of our most powerful tools. So come with us as we dive into the realm of the unseen, where dimensions whisper and reality is far stranger and far more beautiful than we ever imagined. Long before scientists could peer into the depths of space with powerful telescopes or smash particles together in massive colliders, the mathematical groundwork for our multidimensional reality was being laid by a handful of visionary thinkers. The story begins not with a flashy discovery, but with a quiet, theoretical breakthrough in the early 20th century. In 1919, a little-known mathematician named Theodore Kaluza was studying Albert Einstein's revolutionary equations of general relativity, which described gravity as the warping of the 3 dimensions of space and the 1 dimension of time. Kaluza made a daring move. He rewrote those same equations, but he did something astonishing. He added a 5th dimension, a dimension we cannot see, and something incredible happened. From this single, elegant act, the equations for a second fundamental force, electromagnetism, emerged naturally. It was as if by simply acknowledging the possibility of an unseen dimension, 2 completely separate forces of nature were suddenly unified. This idea was further refined by physicist Oscar Klein, who suggested this extra dimension wasn't vast and expansive like the ones we know, but instead was curled up into an unimaginably tiny loop, smaller than an atom. This Kaluza-Klein theory was the first serious scientific proposal that our universe might be built upon more than the dimensions we experience directly. For a time, this beautiful idea was set aside as the physics world became captivated by the strange new realm of quantum mechanics, but the seed had been planted. The notion of extra dimensions refused to disappear, quietly waiting for its moment to re-emerge. That moment arrived decades later with the development of string theory. This ambitious framework proposes that the fundamental building blocks of the universe are not point-like particles, but incredibly tiny, vibrating strings. And for the mathematics of this theory to work, for these vibrations to produce all the known particles and forces, the strings must vibrate in not just 4, but 10 or even more dimensions. This historical journey from Kaluza's bold calculation to the complex edifice of string theory shows us that the search for hidden dimensions isn't a wild guess or a fringe idea. It is a persistent, evolving thread in the tapestry of modern physics, a direct response to some of the most profound questions we can ask. Why are there four fundamental forces? Why do particles have the masses and charges that they do? The drive to answer these questions has pushed physicists to consider realities beyond our immediate perception, building a century-long foundation of mathematical rigor and creative thought. The discoveries we are about to explore are so revolutionary precisely because they don't come out of nowhere. They are the latest chapters in this long and fascinating story, where theoretical prediction finally meets tangible, observational evidence, inviting us all to witness the unfolding of a deeper cosmic truth. Now, let's turn from the quiet world of theoretical prediction to the stunning, observable reality of our universe, beginning with a mystery so profound it forever changed our understanding of gravity itself. It starts with a simple question: how does a galaxy spin? You might picture our own Milky Way, a vast, swirling pinwheel of stars, gas, and dust. Based on everything we know about gravity and motion, the stars at the outer edges of this pinwheel, far from the dense core, should be moving relatively slowly. Just as planets farther from the Sun orbit more slowly than those closer in, this isn't just a guess, it's a direct prediction from Newton's and Einstein's laws. But in the 1970s, astronomer Vera Rubin and her colleagues decided to actually measure this motion. They meticulously studied the rotation speeds of stars in numerous galaxies, and what they found was utterly baffling. The stars on the outskirts were not moving slowly. They were hurtling around at virtually the same incredible speed as the stars near the center. This was like watching a giant merry-go-round where the children on the very edge are spinning just as fast as those right next to the center, defying all logic and physics. The galaxies were spinning so fast that according to our known laws of gravity, they should have simply flown apart, scattering their stars into the void. The fact that they held together meant only one thing: there had to be something more there, something providing an enormous amount of extra gravitational glue to hold these speeding stars in their orbits. Scientists called this missing ingredient dark matter, an invisible substance that does not emit, absorb, or reflect light, yet whose gravitational pull is powerful enough to shape entire galaxies. But what if dark matter isn't just a new type of particle? What if its mysterious nature is a clue to an even deeper reality? This is where the idea of hidden dimensions enters the picture. Some theoretical physicists propose that the gravitational force we feel in our three-dimensional world is actually just a fraction of its full strength. In this view, a significant portion of gravity could be leaking away, spreading out into additional, unseen spatial dimensions that are curled up or warped in ways we cannot perceive. From our limited perspective, it would appear that gravity is unexpectedly weak, unable on its own to account for the rapid spinning of galaxies. The anomaly in the rotation curves might not just be evidence of missing mass, but evidence of gravity itself behaving differently on cosmic scales due to the influence of these other dimensions. It's a radical reinterpretation of Vera Rubin's landmark discovery. She revealed that the universe is dominated by something we cannot see. The next step is to ask if the reason we cannot see it is because it operates in a realm beyond our own, tugging on the fabric of our reality from a hidden dimensional vantage point that we are only beginning to mathematically map. This single observation of galaxies spinning too fast shattered our classical understanding and opened a door to a much stranger and much larger cosmic landscape. While the rotation of galaxies gave us a hint of something missing in the present-day cosmos, our next discovery takes us all the way back to the very beginning, to a fossilized echo of creation itself. This is the cosmic microwave background, or CMB, the oldest light in the universe. It's the remnant heat from the Big Bang, a faint glow that fills every corner of space, a snapshot of the universe when it was just a mere 380,000 years old. For decades, this cosmic afterglow has been a treasure trove for cosmologists, and satellites like NASA, WMAP, and the European Space Agency's Planck have mapped its minute temperature variations with breathtaking precision. These maps reveal a universe that is, for the most part, remarkably uniform, with tiny fluctuations that eventually seeded the growth of all the galaxies and clusters we see today. But nestled within this overall uniformity are a few strange, persistent anomalies that simply don't fit the standard model. The most famous of these is known as the cold spot, a vast, unusually cool region in the sky that is far larger and much colder than our theories can comfortably explain. One proposed solution is that it's not a feature of our universe at all, but a cosmic bruise, the imprint of a collision with another universe in the vast multiverse. This idea, while speculative, directly invokes the concept of other realms existing in dimensions beyond our own. Furthermore, there are large-scale asymmetries in the CMB, a mysterious alignment of certain patterns that seems to suggest a preferred direction in the cosmos, almost as if the universe has a subtle tilt. This challenges the foundational cosmological principle, which states that the universe should look roughly the same in every direction, with no special place or orientation. If the very fabric of the newborn universe shows a handedness or a directional preference, it could be a sign that its development was influenced by something outside its own four-dimensional bounds. Think of our three-dimensional universe as a membrane or a brain floating within a higher dimensional space. The gentle gravitational tug of another, nearby brain in these unseen dimensions could have left a faint imprint on the infant cosmos, warping the distribution of matter and energy in a way that we now detect as these subtle irregularities in the microwave background. It's as if we are examining a perfectly woven tapestry and finding a single thread that seems to originate from outside the loom, hinting at the hand of the weaver. The Planck data didn't just confirm these anomalies, it refined them, making it increasingly difficult to dismiss them as mere statistical flukes. They stand as a quiet, persistent whisper from the dawn of time, suggesting that the initial conditions of our entire reality were set not in isolation, but in conversation with dimensions we are only beginning to conceive of. Now, if the spinning of galaxies and the ancient light of the Big Bang suggest a hidden architecture to the cosmos, our next discovery plunges us into the bizarre and counterintuitive heart of the very small, revealing a connection so strange it seems to defy the universe's own speed limit. This is the phenomenon of quantum entanglement, a concept so profound that even Albert Einstein famously dismissed it as spooky action at a distance. To understand why it so troubled the great physicist, picture this. You create two particles, perhaps two electrons, in a single, unified quantum state. You then carefully separate them, placing one in a lab on Earth and sending the other on a journey to the far side of the Moon. According to the rules of quantum mechanics, these particles remain intimately linked, their fates intertwined. Now you perform a measurement on the particle here on Earth, instantly forcing it to choose a specific property like its spin. And in that exact same instant, without any delay for the time it would take light to travel the distance, its partner on the Moon will snap into the corresponding opposite state. It's as if the two particles are communicating faster than the speed of light, a notion that violates the very core of Einstein's theory of relativity. For decades, this was a philosophical puzzle, a thought experiment highlighting the apparent absurdity of quantum theory. But then a physicist named John Stuart Bell devised a practical way to test it. Bell's theorem provided a mathematical framework to distinguish between a universe where particles have hidden, predetermined states, a notion Einstein favored, and one where this spooky, instantaneous connection is real. When experiments were finally conducted, the results were unequivocal. Time and again, from laboratories around the world, the data confirmed that entangled particles do indeed influence each other instantly, regardless of the vastness of the space between them. This wasn't a flaw in the theory, it was a fundamental feature of our reality. So how can this be? How can information, or what seems like information, travel instantaneously across a void, ignoring the cosmic speed limit set by light? This is where the concept of extra dimensions offers a breathtakingly elegant solution. What if these two particles aren't really communicating across a vast three-dimensional distance at all? Imagine our familiar three dimensions of space are like the flat surface of a sheet of paper. 2 points on that paper can be very far apart, but if that paper is folded through a higher, third dimension, those 2 points could be brought right next to each other. In the same way, entangled particles might not be sending a signal across a long, lonely highway in our space. Instead, their connection could be shortcut through a hidden, higher dimensional bridge, a fold in the geometric fabric of reality that makes them immediate neighbors from a multidimensional perspective. This idea transforms entanglement from a magical-seeming paradox into a geometric phenomenon. The particles aren't breaking any rules, they are simply operating within a richer, more complex spatial rulebook than we can directly perceive. Their instantaneous correlation is the direct physical evidence of that deeper architecture, a hidden web of connectivity woven through dimensions we are only beginning to map mathematically. It suggests that at the most fundamental level, the universe is not a collection of separate objects in empty space, but a deeply interconnected whole, with extra dimensions serving as the unseen threads stitching everything together into a single, coherent tapestry of existence. We've seen how hidden dimensions might explain the spin of galaxies and the whispers from the Big Bang, and even how they could create a secret shortcut for entangled particles. But our next discovery tackles perhaps the most fundamental and puzzling imbalance in all of nature, a question so basic it strikes at the heart of why our universe is built the way it is. It's called the hierarchy problem, and it asks a deceptively simple question. Why is gravity so incredibly weak? Think about it for a moment. The electromagnetic force that holds atoms together, the strong nuclear force that binds atomic nuclei, these forces are powerful, operating on tiny scales with immense strength. But gravity, the force that governs the motion of planets and galaxies, is almost unimaginably feeble by comparison. To see this in action, you don't need a particle accelerator. Just use a simple fridge magnet. When you lift that magnet and let it stick to the door, you are witnessing a tiny, everyday piece of electromagnetism effortlessly overpowering the gravitational pull of the entire planet Earth. That's how weak gravity is. This vast difference in strength, a factor of a 1 followed by 39 zeros, is one of the greatest unsolved mysteries in physics. The standard model of particle physics simply accepts this gap as a given, an arbitrary constant of nature, but to physicists that feels like an unsatisfying answer. It begs for a deeper explanation. This is where the idea of extra dimensions moves from a theoretical curiosity to a potential game changer. What if gravity isn't inherently weak? What if it only seems weak to us? Imagine you are standing on one side of a vast, thick wall, and you can hear only a faint, muffled sound coming from the other side. You might assume the person over there is just whispering, but what if the wall is actually filled with hidden corridors and chambers that absorb and dissipate the sound? The person could be shouting, but from your limited perspective, their voice seems faint. This is the core idea behind one of the most elegant solutions to the hierarchy problem, proposed by physicists Lisa Randall and Raman Sundram. Their model suggests our entire universe of 3 spatial dimensions is a membrane, or a brain, floating within a higher dimensional space. Crucially, this higher dimensional space is not flat or tiny. It is profoundly warped, like a sheet of fabric stretched thin in some places and bunched up in others. In this warped geometry, the particles of the other forces like electromagnetism are stuck to our brain. They are confined to our 3-dimensional world, so their strength is felt here at full power. But the particle that carries the gravitational force, the graviton, is unique. It is not confined to our brain. It can wander into the warped, higher dimensional bulk. From our perspective, this means that a significant portion of the gravitational force is effectively leaking away, dissipating into these unseen dimensions. The gravity we experience is just a tiny, leftover fraction of its true strength, like seeing only the tip of an enormous iceberg. The Randall-Sundram model doesn't just propose extra dimensions, it gives them a specific, warped shape that mathematically accounts for the staggering difference between gravity and the other forces. It turns an arbitrary, baffling number into a natural consequence of the geometry of reality itself. This elegant idea provides a compelling answer to a question that has puzzled physicists for generations, suggesting that the very feebleness of gravity we experience every time we drop a pen or jump in the air is not a fundamental fact but a profound clue. It is a direct signature of a larger, hidden dimensional reality, a silent testament to the fact that our universe is far more expansive and intricately folded than we could ever perceive with our senses alone. The mystery of dark matter presents one of the most tantalizing puzzles in modern cosmology. We know it's there. Its gravitational pull is the invisible hand that sculpts the cosmos, holding fast-spinning galaxies together and guiding the largest structures in the universe. Yet, despite decades of searching, we have never directly seen a single particle of it. It neither emits, absorbs, nor reflects light, making it completely transparent to every telescope we've ever built. This has led scientists on a fascinating quest, not just to find what dark matter is, but to ask a more profound question: why is it so completely hidden from us? One compelling answer emerging from theoretical physics is that dark matter might be hidden in a very literal sense, not just made of invisible particles, but existing in dimensions of space that are permanently beyond our reach. To grasp this idea, we can turn to a framework known as brain cosmology. Imagine our entire visible universe, all the stars, planets, and people, is confined to a 3-dimensional membrane, or brain, like a single slice of bread in a much larger loaf. This brain floats within a higher dimensional space, often called the bulk. The crucial point is that all the ordinary matter and forces we know and love, from the light from a star to the atoms in your hand, are stuck to this brain. They are like ink trapped on the surface of a page, unable to leave. But what if some things aren't stuck? This is where dark matter enters the story. Some theories propose that dark matter particles are fundamentally different. They are not anchored to our brain. Instead, they are free to move and gravitate within the full volume of the higher dimensional bulk. From our perspective, locked onto our 3-dimensional slice, these particles would be almost impossible to detect directly. We could only perceive their gravitational influence, much like you might feel the vibrations of a person walking in the room above you without ever seeing them. Their gravity, bleeding through from the higher dimensional space, would tug on the matter in our brain, providing the extra pull needed to explain the motions of stars and galaxies. This idea elegantly explains why our most sensitive detectors buried deep underground have come up empty. These experiments are designed to look for particles interacting through the weak nuclear force, a force likely confined to our brain. If dark matter is a traveler of the bulk, it simply wouldn't register in the same way. It would pass through our detectors and indeed our entire world as if it weren't there, leaving behind only the faintest gravitational signature. This multidimensional nature of dark matter could also solve other puzzles. For instance, computer simulations of how dark matter should clump together under gravity predict that every large galaxy should be surrounded by a huge number of smaller satellite galaxies. Yet we observe far fewer than these models predict. If dark matter can move through extra dimensions, its gravitational behavior might be subtly different, causing it to clump less efficiently and naturally leading to the galactic landscape we actually see. The dark matter halos that cradle galaxies like ours may not be simple, smooth spheres, but incredibly complex structures shaped by dynamics playing out in a hidden dimensional landscape. Their true form and complexity forever veiled from our sight, yet their gravitational embrace defining the very architecture of the visible universe. For years, the Pioneer 10 and 11 spacecraft served as humanity's most distant robotic ambassadors, hurtling through the void on a one-way journey beyond our solar system. As they traveled farther and farther from the Sun, their faint radio signals were meticulously tracked by teams of scientists here on Earth, allowing for an incredibly precise measurement of their speed and trajectory. And that's when they noticed something deeply strange. Both spacecraft, despite being millions of miles apart, were experiencing a tiny, unexplained deceleration. It was as if an invisible hand was ever so gently applying the brakes, slowing them down by a minuscule amount, about the same as a single grain of sand's worth of force pushing back against a brick. This was the Pioneer Anomaly, a tiny deviation that defied all expectations and calculations. At first, scientists meticulously searched for a conventional explanation. Perhaps it was the gentle push of escaping gas from the spacecraft's own small thrusters, or the subtle pressure of the solar wind. The leading explanation that eventually emerged pointed to heat. The spacecraft's radioactive power sources generated a constant, faint warmth, and this thermal radiation, bouncing off the back of the spacecraft's large antenna dish, could provide just enough of a push in the opposite direction to account for most of the observed slowdown. This seemed to solve the puzzle, closing the case as an interesting but ultimately mundane engineering quirk. Yet, for some physicists, a nagging question remained. Even after accounting for this thermal radiation with increasingly sophisticated computer models, a tiny, residual anomaly seemed to persist. It was a whisper of a signal, a discrepancy so small it could easily be dismissed as a rounding error, but it was consistent across both spacecraft. This opened the door to a much more exotic possibility. What if this minuscule leftover effect wasn't an error at all, but a genuine, previously unknown physical phenomenon? And what if that phenomenon was a clue to the existence of dimensions beyond our own? One compelling idea is that gravity itself might behave differently over extremely large distances or in the near-perfect vacuum of deep space. Our current understanding of gravity, encapsulated in Einstein's theory of general relativity, has been tested with spectacular success within our solar system. But what if, on the scale of the Pioneer's journey, the theory requires a tiny modification? Some theoretical models that incorporate extra dimensions predict exactly that. In these models, the influence of gravity could be subtly enhanced or altered by its interaction with hidden spatial layers, creating an additional, very weak force that only becomes noticeable over vast interplanetary distances where the gravitational pull of the Sun is already incredibly faint. The Pioneer spacecraft, in their lonely voyage, may have been the first human-made objects to travel far enough into the cosmic deep to just barely feel this effect, a faint gravitational tug from a dimension we cannot see. While the thermal explanation remains the most widely accepted, the story of the Pioneer Anomaly is a powerful testament to the scientific process. It shows how even the smallest, most perplexing piece of data can lead us to question our most fundamental assumptions about the universe. It reminds us that sometimes the most profound discoveries are not announced with a bang, but with a barely perceptible whisper from the darkness, a gentle nudge that suggests our maps of reality are still missing a few crucial and perhaps multidimensional details. But perhaps the most profound challenge to our understanding of reality comes from the enigmatic nature of black holes, and a puzzle so deep it threatened to unravel the very foundations of physics. This is the black hole information paradox, a conflict between the two great pillars of modern science, Einstein's general relativity and quantum mechanics. According to Einstein's theory, a black hole is defined by its event horizon, a point of no return from which not even light can escape. If you were to throw an object into a black hole, say, a book containing vast amounts of information, it would be lost forever, crushed into the singularity at the center. The black hole would subsequently evaporate over astronomical timescales through a process known as Hawking radiation, slowly releasing energy back into the universe. But here's the catch. The rules of quantum mechanics are absolute and unwavering. Information can never be truly destroyed. It might be scrambled or become incredibly difficult to read, but it must, in principle, be preserved. So what happens to the information contained within that book? Does it vanish when the black hole evaporates, violating a fundamental law of the universe? Or is it somehow encoded in the Hawking radiation, a possibility that itself creates a host of other logical inconsistencies? For decades, this was more than just an academic debate. It was a genuine crisis in theoretical physics. The resolution to this paradox may be one of the most mind-bending concepts ever proposed, and it points directly toward the existence of hidden dimensions. It's called the holographic principle. This revolutionary idea suggests that all the information that falls into a three-dimensional black hole is not lost inside it, but is instead perfectly encoded on a two-dimensional surface, specifically on its event horizon. Think of it like a hologram. A common security hologram on a credit card is a two-dimensional surface, but it contains all the information needed to project a three-dimensional image. In the same way, the event horizon of a black hole could act as a vast cosmic hard drive, storing a perfect, scrambled record of everything that has ever fallen in, with that information then slowly leaking out in the Hawking radiation over eons. This means the three-dimensional interior of the black hole, with its terrifying singularity, is essentially a projection, an illusion generated by the data stored on its two-dimensional boundary. This is where extra dimensions become crucial. The holographic principle finds its most robust mathematical realization in a concept known as the anti-de Sitter/conformal field theory correspondence, or AD-S/CFD. This is a powerful duality that suggests a gravitational theory operating in a higher dimensional volume like the interior of a black hole is completely equivalent to a quantum field theory operating on its lower dimensional boundary. In simpler terms, a universe with gravity and extra dimensions can be perfectly described as a universe without gravity that has one fewer dimension. Our perception of a three-dimensional world with gravitational forces could, in fact, be a projection from a two-dimensional reality where those forces don't exist at all. This isn't just a nifty trick for black holes. Some physicists like Leonard Susskind have argued it could be a fundamental property of the entire universe. We might be living in a cosmic hologram. The black hole information paradox, once seen as a fatal flaw in our understanding, now serves as a guiding light. It forces us to consider that the dimensions we experience so vividly might not be the full story. The solution requires us to accept that information is not stored where we think it is, but is instead painted onto the lower dimensional fabric of spacetime itself, a concept that only makes sense if we embrace a reality far more interconnected and illusory than we ever dreamed. The event horizon is no longer just a terrifying cliff edge. It is the ultimate Rosetta Stone, a surface that holds the key to translating between a world with gravity and hidden dimensions and a world without. While the black hole information paradox challenges our understanding of information, another profound discrepancy strikes at the very essence of empty space itself. This is the vacuum catastrophe, a problem so severe that it represents the largest mismatch between theory and observation in the entire history of science. To understand it, we must first redefine what we mean by nothing. According to quantum physics, a perfect vacuum is not truly empty. Instead, it is a seething, bubbling foam of virtual particles. These are pairs of particles and antiparticles that spontaneously pop into existence for an unimaginably brief moment, borrowing energy from the vacuum before annihilating each other and disappearing again. This constant, frantic dance is happening everywhere all the time, even in the deepest, darkest voids between galaxies. All this activity imbues empty space with a background energy, known as the vacuum energy density or dark energy. This is where the problem begins. When physicists use the well-established rules of quantum field theory to calculate how much energy this quantum foam should contain, they arrive at an astronomically enormous number. The predicted energy density should be so powerful that it would have caused the universe to expand at a ferocious rate, tearing apart galaxies, solar systems, and even atoms within the first fraction of a second after the Big Bang. Life, and indeed any structure at all, would have been utterly impossible. Yet, when astronomers actually measure the expansion rate of the universe, they find the effect of this vacuum energy is real, but it is incredibly, inexplicably small. The observed value is a factor of 10 to the power of 120 times smaller than the theoretical prediction. That's a 1 followed by 120 zeros. This isn't just a small error, it's a chasm of misunderstanding so vast that it suggests our fundamental theories are missing something critical. This is where the elegance of extra dimensions offers a potential escape from this catastrophic impasse. The key idea is that the vacuum energy we calculate might not be confined solely to our three-dimensional universe. Imagine the quantum foam not as a flat, two-dimensional film on the surface of a pond, but as a vast, multidimensional volume. In this view, the incredible energy predicted by our equations could be the total energy contained within all dimensions, both seen and unseen. But from our perspective, trapped on our three-dimensional brain, we would only be able to perceive or experience the fraction of that energy that leaks into our own spatial layer. The vast majority of the vacuum's intrinsic energy could be dissipating or leaking into the additional, compactified dimensions proposed by string theory and other models. What we measure as the vacuum energy density would then be just the tiny residue that remains in our familiar realm, like hearing only a faint echo of a symphony playing in a distant, enormous concert hall. This multidimensional leakage provides an elegant mechanism to solve the hierarchy problem of vacuum energy. The discrepancy isn't an error in our math, but a profound clue about the architecture of reality. The vacuum catastrophe forces us to confront the possibility that the empty space around us is not a lonely, self-contained void, but is instead intimately connected to a richer, higher dimensional plenum. The energy we observe, which is gently accelerating the expansion of the universe, is merely the three-dimensional shadow of a far more vibrant and energetic multidimensional reality. It suggests that the true nature of the vacuum is not one of absence, but of hidden dimensional abundance, and that aligning our theories with observation requires us to finally acknowledge the full, sprawling dimensional landscape in which our universe is embedded. While the vast scales of cosmology offer one window into the unseen, some of the most compelling evidence for new physics is emerging from incredibly precise measurements of the very small. This brings us to the world of subatomic particles and a property so fundamental it acts like a tiny fingerprint for matter itself, the magnetic moment. Every particle with spin, like an electron or its heavier cousin the muon, acts like a miniature bar magnet. The strength of this magnetism is dictated by a number called the G factor, and for the electron, quantum electrodynamics allows us to calculate this value with staggering precision, to better than 1 part in a trillion. The agreement between theory and experiment for the electron is one of the greatest triumphs of modern physics, a testament to the power of the Standard Model. But when we turn to the muon, the story becomes far more intriguing. Muons are often called fat electrons. They are identical in every way except that they are about 200 times heavier and are unstable, decaying into other particles in a few millionths of a second. This extra mass makes them uniquely sensitive to the fleeting, ghostly influences of any particles or forces that might exist just beyond the reach of our current theories. According to the Standard Model, a muon's magnetic moment isn't defined solely by its own properties. As it travels through space, it is constantly surrounded by a seething cloud of virtual particles blinking in and out of existence from the quantum vacuum. This cloud subtly alters the muon's internal magnetism, creating a tiny, predictable deviation from the simple value it would have in a classical world. Physicists can calculate this so-called anomalous magnetic moment with incredible care, accounting for every known virtual particle, photons, electrons, quarks, and more. Yet, when experimentalists at Brookhaven National Laboratory and now at Fermilab actually measure this value with exquisite precision by watching muons wobble like tiny tops in a powerful magnetic field, they find a persistent discrepancy. The muon's magnetism is ever so slightly stronger than the Standard Model predicts. This tiny anomaly, a difference of about 2.5 parts in a billion, might seem insignificant, but in the hyper-precise world of particle physics, it screams for an explanation. It is a clear sign that the muon is sensing something in its quantum cloud that our equations have not accounted for. This something could be an entirely new type of particle, or perhaps a new fundamental force of nature. But it could also be something even more profound, a signature of hidden dimensions. Theorists propose that the compact, curled-up extra dimensions required by string theory could be influencing the muon's behavior in a detectable way. These dimensions aren't just empty voids. They have a shape and a size that can resonate with the quantum fields of particles. It's possible that the muon's magnetic field could be interacting with or even leaking into these hidden dimensions, creating an additional, subtle contribution to its overall magnetism that our standard calculations simply do not include. The anomaly measured at Fermilab could be the first faint signal of this multidimensional leakage, a whisper from a geometric reality that is woven into the fabric of our own but operates on a scale too small to see directly. The ongoing experiments are pushing the precision to even greater heights, seeking to confirm if this discrepancy is real and to narrow down its exact value. If it holds, it won't just be the discovery of a new particle. It will be a monumental shift in our understanding of reality's underlying structure, proving that the stage upon which particles dance is far grander and more complex than the three-dimensional space we have always taken for granted. The detection of gravitational waves in 2015 was a seismic event in physics, confirming the last major prediction of Einstein's general relativity and opening an entirely new window onto the cosmos. For the first time, we could literally hear the universe, listening to the deep, thrumming chords played by colossal events like the mergers of black holes. The Laser Interferometer Gravitational Wave Observatory, or LIGO, recorded these ripples in spacetime as a characteristic chirp, a rising frequency that peaks in a sudden crescendo and then rapidly fades away into silence, exactly as Einstein's equations predicted. But what if that silence isn't the end of the story? A small group of physicists began to ask a daring question. What if there's an echo? The idea is as fascinating as it is radical. When two black holes collide and merge, they create a new, larger black hole that vibrates like a struck bell, ringing down and settling into its new form. According to standard physics, these vibrations, known as quasi-normal modes, should dampen and disappear smoothly. But some researchers, upon reanalyzing the public LIGO data from several of these monumental events, reported finding something unexpected. They claim to detect faint, repeating signals that appeared just after the main gravitational wave chirp had faded. These were not part of the predicted ring down. They were subtle, persistent echoes, as if the gravitational waves were bouncing off some unseen structure just outside the new black hole's event horizon. The immediate and most conventional explanation was that these were simply glitches in the date, a random noise being misinterpreted by the analysis algorithms. The LIGO collaboration itself has been cautious, stating that the evidence for these echoes is not yet conclusive and requires further verification with more detections. Yet the possibility has ignited the imaginations of theorists. If these echoes are real, what could possibly cause them? One of the most compelling proposals involves the very fabric of space-time and the potential existence of extra dimensions. In some models, the event horizon of a black hole might not be the true point of no return we believe it to be. Instead, it could be surrounded by a theoretical structure called a Planck-scale warp, or a quantum firewall, a region of intensely curved space that acts like a mirror for gravitational waves. This is where higher dimensions come into play. The intense gravity of the newborn black hole could be warping the local geometry of space-time in a way that reveals the underlying presence of these hidden dimensions. The echoes, in this view, would be the gravitational waves from the merger briefly traveling into these extra-dimensional folds and then reflecting back into our own, creating a delayed and repeated signal. It would be akin to shouting into a vast, complex cave system. You hear your initial call, followed moments later by a series of fainter echoes bouncing off walls and chambers you cannot see. The LIGO detectors would be listening for the reverberations from the hidden architecture of the universe itself. The search for these echoes represents a thrilling new frontier in observational physics. It moves us from simply confirming a century-old theory to potentially discovering something entirely new about the fundamental nature of reality. Each new black hole merger detected provides another opportunity to listen more carefully, to refine the analysis, and to either confirm or rule out this extraordinary possibility. While the debate continues, the very fact that we can now pose such a question and search for an answer in the faint ripples of space-time from a billion light-years away is a testament to how far we have come. We are no longer just observers of the cosmos. We are becoming its listeners, and we are beginning to hear whispers that suggest the universe is far more strange and layered than we ever imagined. If the faint echoes from black hole mergers hint at a hidden structure in spacetime, our next discovery points to a potential flaw in one of cosmology's most sacred principles, etched across the entire sky. This is the so-called axis of evil, a name that perfectly captures how unsettling this finding is to our understanding of the universe. The principle it challenges is the cosmological principle, a foundational idea that states the universe on the largest scales should be homogeneous and isotropic. In simpler terms, it should look roughly the same in every direction and have no special place or preferred orientation. It's the reason we don't believe we're at the center of the cosmos. But the axis of evil suggests that on the grandest scale of all, the universe might not be playing by these rules. This axis isn't a physical object but a startling pattern found in the most detailed map we have of the infant universe, the cosmic microwave background. The CMB is a snapshot of the universe when it was just 380,000 years old, and its tiny temperature fluctuations, hot and cold spots, should be randomly distributed like a static-filled television screen. There should be no grand pattern, no overarching alignment. Yet, when scientists from the WMAP and later the Planck satellite missions analyzed this data, they found something that sent a chill through the cosmology community. The largest of these fluctuations, the biggest hot and cold spots, aren't randomly oriented at all. They appear to be aligned along a specific preferred direction in space, a single giant axis that stretches across the cosmos. Even more strangely, this axis seems to be curiously aligned with the plane of our own solar system, a coincidence that feels far too convenient to be random and has left scientists scrambling for an explanation. The immediate reaction was to question the data itself. Could this be an artifact of the way we process the signals, perhaps contamination from our own galaxy's foreground light? Teams have checked and rechecked, using increasingly sophisticated methods to remove any potential sources of error. And while the signal has been slightly diminished, the alignment persists. It refuses to go away. This leaves us with a genuinely radical possibility that the universe does have a preferred direction, a subtle handedness or asymmetry imprinted upon it at birth. This would be like discovering that a supposedly perfectly round ball actually has a barely perceptible seam running along its equator, a fundamental flaw in its symmetry. So how could such a thing happen? How could the entire universe get a tilt? This is where the concept of higher dimensions offers a breathtakingly elegant solution. Imagine our three-dimensional universe as a vast, flat sheet of paper. Now picture that sheet floating within a higher dimensional space, like a single leaf resting on the surface of a pond. If another such leaf, another universe or brain, were floating nearby in that higher dimensional bulk, its gravitational influence could have gently tugged on our infant universe during its earliest, most formative moments. This external pull, acting from a dimension we cannot perceive, would have imparted a subtle preferred direction to the expansion and evolution of our cosmos, warping the distribution of matter and energy in a specific alignment. The pattern we see in the CMB wouldn't be a random statistical fluke. It would be a cosmic bruise, the permanent imprint of a gravitational handshake from a neighboring reality in the vast, multidimensional landscape of the cosmos. The axis of evil, therefore, is more than just a puzzling anomaly. It is a direct challenge to our assumption of cosmic loneliness and a potential pointer toward a far more interconnected existence. It suggests that the initial conditions of our entire reality were not set in isolated perfection, but were influenced by forces and entities from outside our dimensional confine. This single preferred direction across the sky might be the first tangible evidence that our universe is not a solitary island, but one of many in a much richer, higher dimensional archipelago, its entire history subtly shaped by unseen neighbors. These ghostly travelers from the heart of the sun and distant supernova hold a secret that has already shattered part of the standard model of particle physics. They are neutrinos, and their story is one of constant, bewildering transformation. Billions of them are passing through your body every second, emanating from the sun, from cosmic rays hitting our atmosphere, and from the violent deaths of stars. For decades, physicists believed these particles were massless, zipping through the universe at nearly the speed of light and barely interacting with anything at all. But then came a series of landmark experiments deep underground, in vast detectors like Super Kamiok and in Japan, and the Sudbury Neutrino Observatory in Canada. They were designed to catch these elusive phantoms, and what they found was utterly unexpected. The number of electron neutrinos arriving from the sun was only about a third of what the models predicted. It wasn't that the sun was producing fewer, it was that the neutrinos were changing their identity on the way here. This phenomenon is called neutrino oscillation. As a neutrino travels through space, it spontaneously morphs between three different types or flavors: electron, muon, and tau. A neutrino born as an electron neutrino in the solar core might arrive at Earth as a muon neutrino. This chameleon-like behavior has one profound implication: neutrinos must have mass. Only a particle with a tiny, non-zero mass can undergo this quantum metamorphosis. The discovery was so monumental it earned the 2015 Nobel Prize in Physics. But this solved one mystery only to unveil a deeper one. The masses of neutrinos are astonishingly small, far lighter than any other fundamental particle, and the mechanism behind these oscillations themselves contains subtle anomalies that don't always perfectly fit the three-flavor model. This is where the fabric of spacetime itself might be whispering its secrets. The journey of a neutrino is not a flight through empty space, but a passage through the seething quantum foam of the vacuum, a realm where the geometry of reality itself might be more complex than we perceive. Some theoretical physicists propose that the compact, curled-up extra dimensions required by string theory could be influencing this delicate dance of oscillation. Imagine a neutrino not as a simple point-like particle, but as a tiny string vibrating in 10 dimensions. As it moves through our three-dimensional space, its vibrations could resonate with the specific geometry and size of these hidden dimensions. These dimensional resonances would act like a subtle filter or a lens, very slightly altering the probability that the neutrino will be in one flavor state or another after a given distance. The effect would be minuscule, almost imperceptible, buried within the already complex mathematics of oscillation. Yet, next-generation experiments like the Deep Underground Neutrino Experiment, or DUNE, are being designed with unprecedented sensitivity to hunt for these very deviations. They will fire intense beams of neutrinos through hundreds of miles of rock to massive detectors, meticulously mapping the oscillation pattern with a precision never before achieved. If they find a discrepancy, a tiny wiggle in the data that cannot be explained by the standard three-flavor model, it could be the first indirect evidence that the neutrinos are sensing something beyond our dimensional plane. Their oscillations would not just be a property of their own infinitesimal mass, but a reflection of the hidden vibrational landscape of the universe they are traversing. These ghostly particles, which can pass through light years of lead without a single interaction, may be the perfect messengers from the multidimensional frontier, their constant transformations a coded signal about the true, rich architecture of the cosmos. But what if the very act of moving through space in a certain way could fundamentally alter what we see, revealing particles and energy where there was only nothingness before? This brings us to one of the most mind-bending predictions in all of theoretical physics, a concept that ties together the worlds of acceleration, heat, and quantum reality. It's called the Unruh Effect, named after the physicist Bill Unruh, who proposed it in 1976. To understand it, we must first revisit our idea of a vacuum. We often think of empty space as just that empty, a true void, but quantum mechanics tells us this is an illusion. Even in the most perfect vacuum at a temperature of absolute zero, the quantum field is alive with fluctuations. Virtual particles constantly flicker into and out of existence, their brief lives governed by Heisenberg's uncertainty principle. Now, imagine an observer, perhaps an astronaut, floating motionless in this deep, dark void. To them, the vacuum appears empty and cold. They detect no particles, but what happens if that astronaut suddenly fires their rockets and begins to accelerate? According to the Unruh Effect, their experience of reality would change completely. From their new, accelerating perspective, the once empty vacuum would no longer seem empty. Instead, they would find themselves immersed in a warm bath of particles, a genuine heat radiation. The vacuum would appear to them as a thermal field with a temperature directly proportional to their acceleration. The faster they accelerate, the hotter this perceived environment becomes. It's a stunning conclusion. An observer's state of motion directly determines whether they perceive a cold, empty void or a warm, particle-filled plasma. There is no single, objective reality. What you see depends entirely on how you are moving. This bizarre effect arises from the interaction between the accelerating observer and the quantum fluctuations of the vacuum. The relentless acceleration effectively scours the vacuum, stirring up the virtual particles and promoting some of them into real, detectable particles. It's a purely quantum phenomenon, a relative effect that has been notoriously difficult to test experimentally because it requires unimaginable accelerations to produce a detectable temperature. For instance, to see a warmth of just 1 degree above absolute zero, an observer would need to accelerate at a rate 100 quadrillion times stronger than the gravity we feel on Earth. While this puts direct laboratory confirmation out of reach for now, the sheer existence of this theoretical effect forces us to confront a profound question about the nature of reality. If particles and temperature are not absolute properties of space, but are instead dependent on an observer's motion, what does that say about the stage upon which this all plays out? This is where the idea of hidden dimensions offers a fascinating new perspective. The incredible energy required to manifest these particles from the vacuum might not be conjured from nothing within our 3 spatial dimensions alone. Some theoretical models suggest that the Unruh radiation an accelerating observer detects could be, in part, a thermal leakage or emission from these compact, higher-dimensional spaces. The intense acceleration could be effectively unlocking a gateway, allowing the observer to briefly sense the thermal energy contained within the full, multidimensional bulk of reality, not just a fraction of it that exists in our familiar 3-dimensional slice. The warmth they feel would be the heat of the entire multidimensional universe, a warmth that is always there but is only perceptible from a specific, accelerated frame of reference. This transforms the Unruh effect from a curious thought experiment about relativity into a potential probe for the hidden geometry of the cosmos. It suggests that the fabric of space-time may have a rich thermal texture that is woven through dimensions we cannot normally access, and that by changing our motion, by accelerating, we can brush against this deeper, warmer layer of reality. It is a powerful reminder that our perception is limited, and that the true nature of the universe might be felt not by who is looking, but by how they are moving. While the Unruh effect shows us how motion can conjure particles from the void, another astonishing quantum phenomenon makes the invisible energy of empty space tangible in a far more direct and measurable way. This is the Casimir Effect, a mysterious force that emerges from nothingness itself, and one that might be subtly shaped by the hidden architecture of reality. To see it in action, picture a perfect vacuum, a region of space utterly devoid of all matter, stripped of every single atom and particle. Now, place two incredibly smooth, uncharged metal plates into this void, bringing them exquisitely close together, separated by a gap narrower than a single wavelength of light. According to the classical physics of the everyday world, nothing should happen. There is no gravity, no electricity, no obvious force to act between them. Yet something incredible occurs. The plates are irresistibly pulled together by a faint but undeniable force. This force doesn't come from anything we can see or touch. It arises from the seething quantum vacuum that fills all of space. Even in a perfect void, the laws of quantum mechanics dictate that fields cannot be perfectly still. They are constantly fluctuating. These quantum fluctuations manifest as a frenzied dance of virtual particles blinking in and out of existence everywhere all the time. Normally, this activity is perfectly balanced, creating no net force in any direction. But when you insert two plates, you change the rules of the game. The plates act like boundaries, restricting the kinds of quantum fluctuations that can occur in the gap between them. Only those fluctuations whose wavelengths fit perfectly between the plates, like musical notes resonating in a pipe of a specific length, are allowed to exist there. Outside the plates, in the boundless void, quantum fluctuations of all wavelengths are free to frolic. This creates a pressure imbalance. The riot of activity on the outside of the plates pushes them together with more force than the limited, quieter fluctuations operating in the narrow gap between them can push them apart. The result is a net inward force, a tangible attraction generated purely by the difference in the quantum vacuum energy on either side of the plates. It is a direct physical manifestation of the energy inherent in nothingness. Scientists have measured this Casimir force with remarkable precision, and it matches the predictions of quantum field theory beautifully. But as experiments have become more sophisticated, probing ever smaller distances and different geometric configurations, some intriguing subtleties have emerged. The force doesn't always behave exactly as the simplest calculations predict, and these tiny discrepancies are where the whispers of extra dimensions might be heard. The standard model calculations for the Casimir effect assume that space between the plates is perfectly smooth and continuous, defined only by the three dimensions we know. But what if, at the almost unimaginably tiny scales being probed, scales smaller than a billionth of a meter, the geometry of space isn't so simple? This is the realm of string theory and other models that propose the existence of additional spatial dimensions, curled up into sizes far smaller than an atom. If these compact dimensions exist, they would add a whole new layer of complexity to the quantum vacuum. The fluctuations would not just be happening in the three-dimensional gap between the plates, they would also be vibrating within these hidden, microscopic folds. This would effectively increase the number of ways the vacuum can fluctuate, subtly altering the balance of forces. The presence of these extra dimensions could either enhance or diminish the Casimir force in a way that depends on the distance between the plates and the specific size and shape of the hidden dimensions. It would be like listening to a symphony in a small, acoustically dead room versus a vast, reverberant cathedral. The same instruments would produce a different sound because of the hidden architecture of the space. Experiments designed to measure the Casimir force with extreme precision, particularly at these sub-micron distances, are effectively listening for the acoustic signature of these hidden dimensional chambers. A deviation from the expected force, however minute, could be the first experimental hint that the quantum vacuum is not a featureless three-dimensional sea, but a multidimensional ocean whose deepest currents flow in directions we are only beginning to imagine. The gentle, invisible pull between two metal plates in a vacuum becomes more than just a quantum curiosity. it transforms into a potential micrometer, a tool for measuring the true, full-dimensional geometry of the void. We have explored how the quantum foam of empty space and the gentle pull of the Casimir effect might be shaped by hidden spatial dimensions, but what about the very fabric of time itself? Could our perception of time as a single, uniform river flowing from past to future be an illusion, a limited view of a far more complex temporal landscape? This brings us to one of the most precise and profound tests in all of modern physics, a search for anomalies in the one thing we believe is constant for everyone, the ticking of the clock. According to Einstein's theory of relativity, time is not absolute. It can stretch and warp. We see this confirmed every day with GPS satellites, whose atomic clocks must be constantly corrected because time for them, orbiting high above Earth, passes ever so slightly faster than it does for us on the surface due to the planet's gravity. This is gravitational time dilation, a well-understood and verified phenomenon. But what if there are other, far stranger sources of time dilation that our current equations cannot account for? This is the frontier of precision metrology, where scientists use the most accurate clocks ever built to hunt for the faintest whispers of new physics. These aren't ordinary clocks, they are optical atomic clocks so precise they would lose less than a single second over the entire age of the universe. They work by using lasers to measure the vibration frequency of atoms, often cesium or strontium, which act as a pendulum swinging with unimaginable regularity. The consistency of this atomic tick is the bedrock of our modern world, governing everything from financial markets to the internet. Yet, when these clocks are compared with each other over long periods, or when their ticks are measured in different orientations or locations, physicists sometimes see incredibly tiny, persistent discrepancies. The clocks don't quite agree with each other, and the differences, while minuscule, are larger than the known margins of error. It's as if time itself is stuttering, fluctuating in a way that defies our current understanding. One compelling explanation for these anomalies ventures into the realm of extra dimensions. The proposal is as radical as it is fascinating. What if these fluctuations are not a flaw in our clocks, but a genuine feature of reality? What if time, as we experience it, is not isolated to our four-dimensional space-time continuum? Perhaps the flow of time can subtly leak into or be influenced by other dimensions where time itself might operate by different rules or even flow at a different rate. In such a model, our timeline would not be a solitary stream, but one of many currents in a vast, multidimensional temporal river. The tiny discrepancies in our atomic clocks could be the result of this temporal interaction, moments when our timeline briefly brushes against another, causing a detectable shudder in the otherwise perfect rhythm of atomic vibrations. To test this, experiments are being designed that are mind-boggling in their precision. Imagine placing two identical atomic clocks at different heights, or orienting them at right angles to each other, and then monitoring them for years, searching for a correlated drift in their timekeeping that cannot be explained by gravity, velocity, or any known environmental factor. Any such persistent, unexplained drift would be a potential signal, a fingerprint of an interaction with a hidden dimension where the fundamental constants governing time might be slightly different. These experiments are effectively using time itself as a detector, turning the entire Earth into a laboratory to probe the hidden structure of reality. The quest is to determine if our experience of time is truly our own, or if it is a local phenomenon, subtly and constantly being influenced by unseen temporal dimensions just beyond the reach of our perception, a discovery that would forever change our understanding of past, present, and future. This brings us back to the very heart of quantum weirdness, to a puzzle so deep that it once led Einstein to question the completeness of the theory itself. We've already touched on the spooky connection of entangled particles, but the EPR paradox, named for Einstein, Podolsky, and Rosen, frames this mystery in its most stark and philosophical form. The paradox isn't just about the instantaneous correlation. It's about what that correlation implies for our understanding of reality. Einstein's core objection was that if the outcome of a measurement on one particle immediately determines the state of its distant partner, then one of two deeply unsettling things must be true. Either the particles must be communicating faster than light, violating relativity, or the properties of the particles were predetermined from the moment they were created, meaning the universe is fundamentally deterministic and our quantum description is incomplete. He favored this second option, believing in a reality that was local and real, where objects have definite properties independent of observation, and no spooky action could occur. For decades, this was a compelling philosophical argument. But then, as we discussed, John Bell provided a way to test it, and the experiments came down decisively against Einstein's local realism. The universe, it seems, is either non-local, allowing for instantaneous influences, or it is not real in the way we classically imagine. This is the uncomfortable conclusion most physicists have had to accept. But what if there is a third option, one that Einstein himself might have appreciated? What if the paradox isn't a paradox at all, but merely a limitation of our three-dimensional perspective? This is where the concept of higher dimensional bridges offers a breathtakingly elegant resolution. The problem of non-locality only exists if we insist that the two entangled particles are truly separate and distant within the confines of our three spatial dimensions. But imagine if those three dimensions are not the full extent of reality. Picture our universe as a two-dimensional sheet of paper with 2 points drawn far apart. From the flat perspective of the paper, the distance between them is vast. But if that paper is curved or folded through a third dimension, those 2 points could be brought into immediate contact. In exactly the same way, two entangled particles that appear separated by a light years of empty space in our three-dimensional view might, in fact, be immediate neighbors when viewed through the lens of a higher dimensional geometry. Their connection isn't a signal speeding through our space. It is a geometric fact, a fundamental closeness in a spatial dimension we cannot perceive. The higher dimensional bridge acts as a cosmic shortcut, making a mockery of what we call distance. This reinterpretation doesn't just solve the communication problem, it restores a form of locality and reality that Einstein would have recognized. The properties of the particles don't need to be communicated because they are part of a single, connected geometric structure in a higher dimensional space. There is no spooky action at a distance because, from the true multidimensional perspective, there is no distance between them to act across. This view embeds the weirdness of quantum mechanics into a broader, more intuitive geometric framework. The strange probabilities and superpositions of quantum theory start to look less like abstract mathematical rules and more like the natural consequences of a reality that has more spatial layers than we can see. The particles aren't defying logic, they are obeying the logic of a higher dimensional universe, and we are only seeing a flattened, projected shadow of their true interaction. This geometric approach doesn't just resolve an 80-year-old paradox, it provides a powerful new language for describing quantum phenomena, suggesting that the true nature of reality isn't weird, it's simply bigger, and our limited perception is what makes it appear strange. The EPR paradox, once a formidable challenge to quantum theory, becomes a crucial clue, a signpost pointing directly toward the existence of a hidden spatial architecture that connects all things. For most of the 20th century, astronomers believed they understood the ultimate fate of the cosmos. After the initial fireball of the Big Bang, the universe had been expanding, but the relentless pull of gravity was thought to be acting as a cosmic brake, gradually slowing this expansion down. The great debate was whether that gravitational tug would be strong enough to one day reverse the expansion, leading to a big crunch, or whether the universe would simply coast forever, expanding at an ever-slowing rate. Then, in the late 1990s, two independent teams of researchers made a discovery so shocking it would win them the Nobel Prize and fundamentally rewrite the story of the cosmos. By meticulously measuring the distances to incredibly far-off supernova, they found that the expansion of the universe wasn't slowing down at all, it was speeding up. Some mysterious, repulsive force was acting against gravity, pushing galaxies apart at an ever-increasing rate. This unknown driver was dubbed dark energy, and it constitutes about 68% of the entire energy content of the universe, making it the dominant force shaping our cosmic destiny. But what is it? The leading hypothesis is that it is a property of space itself, a constant energy density inherent to the vacuum, often represented by Einstein's cosmological constant. But this simple explanation leads directly to the vacuum catastrophe, that staggering mismatch between prediction and observation we discussed earlier. If the cosmological constant is the answer, its value is unnaturally, inexplicably small. This has led physicists to explore far more dynamic and exotic possibilities, and some of the most compelling involve the influence of unseen dimensions. One of the leading alternative ideas is a concept known as quintessence. Unlike a static cosmological constant, quintessence proposes that dark energy is a dynamic field, a kind of fifth fundamental force that permeates all of space. This field can evolve over time, its strength waxing and waning, which could explain why the acceleration of the universe appears to have begun dominating over gravity only relatively recently in cosmic history. But where could such a field originate? This is where the geometry of higher dimensions provides a powerful and elegant source. Imagine our four-dimensional space-time not as an isolated entity, but as a dynamic membrane vibrating within a higher dimensional bulk. The vibrations and oscillations of our brain, or the influence of other brains in this bulk, could generate fields that permeate our entire universe. A quintessence field could be precisely such a phenomenon, a vibration in the higher dimensional geometry that manifests in our world as a smooth, repulsive energy causing space itself to stretch at an accelerating rate. Think of it like a drumhead. When you strike a drum, the two-dimensional surface of the drumhead vibrates, creating sound waves that travel through the three-dimensional air around it. In a similar way, the dynamics of higher dimensional space could be causing our four-dimensional universe to vibrate, and the dark energy we measure is the cosmic sound of that vibration, a pressure that pushes the fabric of space-time apart. The acceleration isn't driven by something within our universe, but by the gentle, persistent influence of the larger dimensional arena in which our universe is embedded. Furthermore, the specific properties of these extra dimensions, their size, shape, and how they are curled up, would determine the strength and behavior of this dark energy field. This offers a potential explanation for why the measured energy is so faint. The effect we see in our three spatial dimensions might be only a tiny, diluted fraction of the total energy involved in the higher dimensional dynamics, much like how the gentle ripple on the surface of a pond is only a small expression of the energy from a stone dropped into its depths. This multidimensional view of dark energy transforms it from a mysterious, isolated number in our equations into a natural consequence of a richer cosmic environment. The relentless acceleration of the universe, which otherwise seems like a lonely and ultimately bleak fate leading to a cold, dark, and empty cosmos, becomes something far more profound. It becomes a signal, It is the most large-scale evidence we have that our universe is not floating in isolation. Its very expansion, the central narrative of all existence, is being subtly guided by the invisible hand of higher dimensions, a constant reminder that the true workings of reality extend far beyond the limits of our perception. Of all the signals ever received from the cosmos, none has captured the public imagination or baffled scientists quite like the WOW signal. It was August 15, 1977, and a radio telescope known as the Big Ear at Ohio State University was silently scanning the skies, part of the ongoing search for extraterrestrial intelligence, or SETI. The system worked by printing out columns of alphanumeric characters on wide, green bar computer paper, representing the signal strength from different points in the sky. For the most part, the printout was a monotonous sea of noise, filled with ones and twos and the occasional four. But at 10:16 that evening, something extraordinary happened. The telescope's receiver passed over a patch of sky in the constellation Sagittarius, and for exactly 72 seconds, the precise window the telescope was designed to monitor any given point, the signal strength skyrocketed. It was so powerful that the volunteer who later discovered the data, astronomer Jerry Amon, circled the sequence of 6 characters 6EQUJ5 and in the margin simply wrote, "Wow." The signal's intensity was off the charts, coming in 30 times stronger than the background noise of deep space. It was narrowband, focused on a specific frequency near 1420 MHz, a quiet channel known as the hydrogen line that scientists had long speculated would be a logical choice for interstellar communication because it's naturally quiet and significant to the most common element in the universe. It appeared and then it vanished, despite decades of concerted effort to find it again. Using increasingly powerful telescopes, the WOW signal was never repeated. It remains a singular, enigmatic event, a one-time shout from the void that defies easy explanation. The most tantalizing possibility, of course, is that it was a transmission from an intelligent extraterrestrial civilization, a fleeting hello that we happened to catch at just the right moment. But the lack of any repeat signal makes this difficult to prove, leading to a host of other natural explanations, from a comet emitting hydrogen that happened to pass through the field of view to a signal from a distant human satellite reflecting off a piece of space debris. Yet, each of these prosaic answers has its own flaws and inconsistencies, leaving the door open for a far more exotic interpretation. What if the WOW signal wasn't a deliberate broadcast traveling through the vast three-dimensional distances between stars, but something even stranger? What if it was a transient, accidental leakage from a dimension adjacent to our own? Imagine our universe as a calm, flat lake. Most signals, whether natural or artificial, are like ripples moving across the surface of that lake. But every once in a while, a powerful event in the depths below, in the higher dimensional bulk surrounding our universe, might cause a splash that briefly breaks the surface, creating a sudden, intense, and isolated ripple that appears to come from nowhere and vanishes just as quickly. The WOW signal had all the characteristics of such a splash. Its incredible strength and its narrowband frequency could be consistent with a coherent, high-energy event. Its one-time only nature is exactly what we might expect from a transient dimensional phenomenon, a chance alignment or a temporary warp in the geometry of space-time that allowed a signal or energy from a hidden dimension to briefly bleed into our own. This idea connects to concepts in brain cosmology, where our universe is a three-dimensional membrane floating in a higher dimensional space. If another such brain passed close to ours, even for a moment, the interaction could generate an immense amount of energy. This energy might manifest in our universe as a burst of radiation across a specific frequency band, a cosmic flashbulb that pops and is gone forever. Alternatively, the signal could be an echo. Just as gravitational wave echoes might bounce off extra-dimensional structures, a powerful electromagnetic event in another dimension could have created a standing wave that briefly resonated through the multidimensional bulk, and our radio telescopes happened to be pointed at the right point in the sky at the exact moment that resonance peaked in our own brain. The WOW signal's unique properties make it a perennial outlier, a data point that refuses to be neatly categorized. While Occam's razor suggests we should favor a natural, if unusual, explanation within our known physics, the signal's stubborn mystery serves a vital purpose. It keeps our minds open to possibilities that lie beyond our current paradigms. It reminds us that the cosmos is capable of surprises that defy our expectations, and that some of the most compelling evidence for a multidimensional reality might not be found in the predictable rhythms of particle physics or the smooth expansion of spacetime, but in the singular, unrepeatable anomalies, the cosmic one-hit wonders that challenge us to think bigger and listen more carefully. The whispers from the other side. For over a century, physics has been governed by two monumental theories, each spectacularly successful in its own domain, yet utterly incompatible with the other. On the one hand, we have general relativity, which describes the force of gravity as the graceful curvature of spacetime by mass and energy, governing the dance of planets and the expansion of the entire cosmos. On the other, we have quantum mechanics, which captures the bizarre, probabilistic behavior of particles and forces at the smallest scales, a world of uncertainty and spooky connections. The problem is that these two theories speak completely different mathematical languages and break down when forced to confront one another, most catastrophically at the center of a black hole or the first moment of the Big Bang, where densities are infinite and our equations simply give up. This great schism is the single most important unsolved problem in fundamental physics, and the quest to heal it, to find a theory of quantum gravity, is the holy grail of modern science. The most promising paths toward this unification all share a common, startling feature. They require us to fundamentally rethink the nature of spacetime itself, and in doing so, they almost universally point toward the existence of a hidden dimensional architecture woven into the very fabric of reality. One of the leading contenders in this grand quest is a framework known as loop quantum gravity. Unlike string theory, which proposes that the fundamental building blocks are tiny vibrating strings, loop quantum gravity suggests that spacetime itself is not smooth and continuous, as Einstein believed, but is instead granular, composed of tiny, indivisible loops or networks of excited gravitational fields. Think of it this way: if you look at a smooth piece of fabric, it appears continuous. But if you zoom in with a powerful enough microscope, you see that it is actually woven from individual, discrete threads. Loop quantum gravity proposes that spacetime has a similar atomic structure. These fundamental threads of spacetime are woven into a network, and the geometry of our universe emerges from the way these loops connect and interact. This approach brilliantly avoids the infinities that plague other theories, and even offers a compelling vision of the Big Bang not as a singularity, but as a big bounce from a previous universe. But to achieve this, the theory must describe these quantum states of geometry, and the mathematics that does this naturally incorporates a concept of background independence, which is a sophisticated way of saying that the theory doesn't require a pre-existing stage for physics to play out on. The stage itself is built from the actors, the loops. This profound reimagining of spacetime as a dynamic quantum network implicitly suggests that what we perceive as 3 dimensions of space and 1 of time is a large-scale illusion, a smooth average of a vastly more complex, microscopic structure that might have many more degrees of freedom, a hidden dimensionality that is only apparent at the Planck scale. String theory, the other great candidate for a theory of everything, makes this dimensional imperative explicit and unavoidable. For the mathematics of string theory to be consistent, to avoid nonsensical probabilities like negative chances of an event occurring, it requires that spacetime has exactly 10 dimensions. We experience only 4, so the theory posits that the other 6 are compactified, curled up into an unimaginably tiny, complex shape called a Kaluza-Klein manifold, a name that hides a universe of intricate geometric possibility. The specific way these extra dimensions are curled up determines the laws of physics in our observable 4-dimensional world, from the number of particle families to the strength of fundamental forces. The search for quantum gravity in string theory is, in many ways, the search for the correct Kaluza-Klein shape. Furthermore, string theory naturally includes gravitons, the hypothetical particles that carry the gravitational force, and successfully describes their quantum behavior without the infinities that sink the standard approach. This success comes at a cost, the acceptance that reality has many more dimensions than we can see. The theory suggests that what we call a particle is actually the different vibrational mode of a string vibrating in this higher dimensional arena. Gravity, and indeed all of reality, is literally the music of these multidimensional strings. The need for extra dimensions in quantum gravity is not just a mathematical quirk. It is a conceptual necessity for taming the wild infinities that appear when gravity is forced into the quantum realm. These frameworks suggest that the sharp, point-like singularities predicted by classical general relativity are actually smoothed out by the underlying quantum structure, whether it be loops or strings. A black hole singularity isn't an infinitely dense point, but an extremely dense, fuzzy region where the classical concept of space and time dissolves into a foam of quantum possibilities, a state where the distinction between different dimensions may blur or become irrelevant. The hidden dimensions in these theories are not just added on, they are fundamental to their very consistency, providing the necessary mathematical and conceptual room for gravity and quantum mechanics to finally shake hands. The search for experimental evidence is incredibly challenging, as these effects are believed to occur at the Planck scale, a realm far beyond our current direct probing capabilities. However, the next generation of gravitational wave detectors and ultra-high-energy cosmic ray observatories may just be able to see the faint imprints of this quantum foam or the subtle effects of extra dimensions on the propagation of spacetime ripples. The quest for quantum gravity is more than an academic exercise. It is a journey to understand the true, deep structure of reality, and every signpost on that journey points toward a universe of hidden dimensions waiting to be discovered. From the quest to unify gravity and quantum mechanics, we arrive at perhaps the most radical and mind-bending idea on our list, a concept that stretches from the farthest frontiers of theoretical physics into the realm of pure philosophy. This is the simulation hypothesis, the proposition that our entire reality, with all its richness and complexity, is not base reality at all, but an incredibly sophisticated simulation, a projection running on some kind of cosmic computer. While this might sound like the plot of a science fiction movie, it's a serious idea debated by philosophers, technologists, and even some physicists, and it finds a surprising, and perhaps unsettling, amount of support from the very physics we've been exploring, particularly the holographic principle and the ad/CFT correspondence. The core argument is often presented through a technological lens. If we assume that civilizations advance and that computing power continues to grow exponentially, then at some point in the far future, a sufficiently advanced civilization, might possess the ability to run incredibly detailed simulations of conscious beings within a virtual reality. If such a civilization ran even a vast number of these simulations, the number of simulated minds could vastly outnumber the number of minds in the original base reality. Therefore, statistically speaking, if you are a conscious being, the odds are far greater that you exist inside one of these countless simulations rather than in the original reality. It's a probabilistic argument that is both compelling and deeply strange, suggesting we might be living in a grand, cosmic ancestor simulation. But where does this connect to physics and hidden dimensions? The bridge is built by the anti-de Sitter/conformal field theory correspondence, or AD-S/CFT, which we encountered with the black hole information paradox. This is a concrete mathematical duality that shows a gravitational theory operating in a volume of space with certain properties is completely equivalent to a quantum field theory operating on the lower dimensional boundary of that volume. In the most famous example, a string theory operating in a five-dimensional universe is perfectly described by a supersymmetric quantum field theory on its four-dimensional boundary. There is no difference between the two descriptions. They are the same reality expressed in two different languages. This means that all the information needed to describe everything happening within that five-dimensional universe, every star, every planet, every person, is entirely encoded on its four-dimensional boundary. The world we would experience as being full of volume, depth, and gravity is, from another perspective, just a vast amount of information painted on a distant, lower dimensional surface. It is, in the most literal physical sense, a hologram. This doesn't prove we are in a simulation, but it does something perhaps more profound. It demonstrates that our intuitive understanding of reality as a three-dimensional, volumetric experience is not fundamental. Physics itself is showing us that a world that feels solid and spatial can be a projection from a reality with completely different rules and a different number of dimensions. The AD-S/CFT correspondence provides a mathematically rigorous example of how a lower dimensional system can contain all the information necessary to generate a higher dimensional reality. If this is possible within the laws of physics, then the jump to a civilization using technology to run such a simulation doesn't seem quite as far-fetched. The universe, according to this view, already contains the blueprints for its own potential simulation. This idea blurs the line between physics and metaphysics, between science and philosophy, in a way that is both thrilling and deeply unsettling. It challenges the very notion of what is real. If our reality is a holographic projection or a simulation, then the laws of physics we are trying to discover are not the fundamental laws of the base reality, but merely the programmed operational rules of the simulation, much like the laws of gravity inside a video game are a simplified code written by the programmers. The search for a final theory of everything would then be the search for the source code of our particular universe. The anomalies and constants we can't explain, from the strength of gravity to the value of the cosmological constant, might not be deep truths waiting to be found, but simply initial parameters set by the creators of the simulation. This is not to say that science is futile, far from it. It simply means that the reality we are probing may be a derived reality, a shadow cast by a deeper, and perhaps utterly alien, truth existing in a higher dimensional realm or on a vast, cosmic two-dimensional hard drive we call the boundary of the universe. From the mind-bending dance of entangled particles to the silent, gravitational grip of dark matter shaping entire galaxies, these 20 discoveries paint a portrait of a cosmos infinitely more complex and wondrous than we ever dared to dream. They are not just isolated curiosities, They are interconnected clues, each one a thread in a grand tapestry that hints at a reality woven with more dimensions than we can directly perceive. This journey through cosmic anomalies and quantum whispers shows us that the universe is not simply stranger than we imagine. It is stranger than we can imagine, constantly challenging the limits of our understanding and inviting us to look deeper. The true revelation here is not just about hidden spatial dimensions, but about the power of human curiosity itself. It is our relentless questioning, our refusal to accept superficial answers, that has brought us to the brink of this new frontier. Every anomalous galaxy rotation curve, every inexplicable whisper in the cosmic microwave background, is a testament to the fact that our scientific models are not failures when they encounter paradox, but are instead evolving, getting closer to a truth that is fundamentally larger than our classical senses. These discoveries remind us that science is not a set of fixed answers, but a living, breathing process of exploration. It is a conversation with the universe, one where we propose ideas through mathematics and experimentation, and the cosmos responds with puzzles and mysteries that push us to think even bigger. The fact that we can even conceive of these higher dimensional concepts and then go looking for their fingerprints in the data from particle colliders and space telescopes is one of the most profound achievements of our species. We are beginning to listen to the subtle music of the cosmos, and we are hearing harmonies that suggest a symphony playing in a hall of many more dimensions than we once thought possible. So as we stand at this threshold, gazing into the unknown, let these ideas spark your own sense of wonder. Let them remind you that the universe is still full of secrets waiting to be uncovered. We encourage you to share which of these discoveries you find the most compelling in the comments below. Was it the holographic solution to the black hole paradox, or the tantalizing possibility of gravitational wave echoes? Let's continue the conversation. If you've enjoyed this journey to the edge of understanding, make sure to subscribe and hit the notification bell so you don't miss our next exploration into the mysteries of space, time, and existence. The greatest discoveries are still ahead of us, hidden in the data, waiting in the void, and written into the fabric of dimensions we have only just begun to imagine. The cosmos is waiting. What will we discover